Tes2al is a centralized chatting application that utilizes steganography by hiding the content of messages in images, ensuring the confidentiality between both initiator and recipient. The application is composed of a lobby chat room where all users can send and receive broadcast messages. In addition, a user may choose any other online user and start a private chat with them. The application is secured using different security elements, including user authentication, hashing, encryption using AES, and key exchange using Tes2al. My name is Laila.
And my name is Mona.
And we were responsible for working on the server-client protocol. Any data sent or received between the client and the server is folded into a JSON object, as so. This JSON object is made up of 3 fields: code, user, and message. Code carries the type of the message exchanged. So we have 16 types of messages, and Mona is going to tell you more about them.
Okay, so looking at the code here, these are the 16 types of messages. So 9 of them is used for the authentication related codes, and the rest are used for the sending and receiving of messages. So for example, the broadcast code, this one is used for broadcasting messages. The private one is for the private messages sent between the user and the client. And there is, for example, the listing users, which is used by the client to request to know all the users that are currently online.
Alright, so the second field is the user field. So the user field is either empty or contains a username depending on the type of messages being sent. For example, when the client sends a private message to the server, the username is that of the recipient. However, when the server sends back the message to the recipient, the user field of this message carries the username of the sender. Similarly, the message field, that one, it also carries a value that is dependent on the message type. This value is encrypted using AES, and it might carry the hashed password of the user, for instance, or the body of the message being sent.
So looking at the code, for example, if we get the scenario of a user wanting to open a new chat with another user, so here for the client it would send in the code that it wants to open a new window. For the user it would send the recipient, and then for the message an empty one. Then at the server side it would go and check in the handling client method. When the code is in a new window, it would go on and look at the user and then checks if that user is already in the client socket, so it's an online one. If it's an online one, either it's the same user, in that case it would send an error message to the client informing him that he cannot talk to himself. Otherwise it would tell each client to open a new window so they could start chatting with each other.
Each of the 3 fields values is hidden in an image. As you can see, this one, and that one. And the 3 images are then folded into this JSON object that is called data, and this JSON object is then sent to its destination.
Hello, my name is Salma, and I'm going to be speaking about how we implemented the authentication in our chatting application. We enforced user authentication through login sign-up page, where users have to send sign-up or login requests in order for them to join the chat room. The sign-up request carries the user's chosen username and hashed password. If the authentication request was approved, the user is then logged in and can start sending messages. I'm going to be going through the sign-up and the login in more details now. For a user to sign up, they have to choose 2 things, a username and a password. There are some constraints, however, on their choice. For example, the username cannot include spaces, and the password has to be at least 8 characters long. We can see this here, that the provided username cannot have any spaces. Otherwise, there will be an error saying that it's invalid, and the password has to be at least 8 characters long, otherwise it will be too short. The password is sent to the server hashed with a randomly generated salt using SHA-512. This can be seen here in the hashing function. The hashing adds an extra layer of security to block any password disclosure attempts made by unauthorized entities, for example, man in the middle, or unauthorized access to the database. The added salt ensures that if two users enter the same password, they would be hashed differently, and therefore preventing any kind of dictionary attack or popular password attack. The server checks if the username already exists in its database. If so, the server sends back an error message to the user prompting them to choose a different username. If not, the server inserts the user's credentials into the database, sends to the user an approval message, and adds the user to the list of current active users. This can be seen here. The server checks if the username already exists in the database. If it does not exist, the server adds it to the database, adds the user to the currently active users list, and sends an approval message to the client. Now I'm going to be explaining the login. The user's entered usernames and passwords are processed in 4 phases in order to grant them access to the chat room. First off, a message containing the username is sent to the server. The server then checks if the username already exists in the database. If so, it extracts the salt from the corresponding hashed password and sends it back to the client. The client uses the salt to hash the provided password and sends it back to the server, which by turn compares the incoming hashed password with the stored one. In case of a match, the server sends an approval to the user and adds the user to the currently active users list. If an error is encountered at any of these phases, the server sends a descriptive error message back to the user. So in the client side, as we can see here, the client sends a request with their username. The server checks if the username exists, and if it exists, it extracts the salt and sends it to the client. The client receives the salt from the server, hashes the password, and sends it back to the server. The server receives the hashed password, compares it with the stored hashed password, and if there is a match, it sends an approval to the client, otherwise it sends an error.
Hi, my name is Alaa and I'm going to explain how we implemented the encryption. All messages are encrypted and decrypted using the AES algorithm we imported from the crypto library. To generate a symmetric key, one that's shared between each client and the server, we used the Diffie-Hellman algorithm. Given a shared prime number and a shared place, each entity generates a pair of public-private keys. The private key is a 16-bit randomly generated number from which the public key is calculated. The public key is exchanged so that each entity can calculate the shared symmetric key given their own secret key and the other entity's public key. The shared key, however, is a number, so we hashed it using SHA 256 to produce a fixed length string that can be used as a symmetric key for the AES. As you can see here, the private key is generated randomly. Then we used it to calculate the public key given the shared place and the shared prime number. After that, each entity can calculate the shared symmetric key given their own private key and the public key of the other entity, and given, of course, the shared prime number. The resulting shared symmetric key is then hashed using SHA 256. Since we need the key length to be 64, we just take half of the hashed string to be the symmetric key used for AES. The encryption works as follows. We first add padding characters so that the length of the message would be a multiple of 16. Then we encrypt it and return the encrypted message. The decryption works similarly. We decrypt the message and then remove any padding characters and then return the decrypted message.
Hi, this is Mariem Qandil.
And this is Hoda.
We were the ones in charge of the steganography part. As we previously mentioned, steganography is the practice of concealing a file within another file. In our case, messages are concealed within images. It's different from cryptography in the sense that cryptography makes the message meaningless, while steganography hides the existence of the message altogether. A famous historical example of steganography is where the original message is written using an invisible ink and hidden among the body of another fake message.
The advantage of using steganography over cryptography alone is that messages do not attract attention to themselves. If you have plainly visible encrypted messages, this is bound to not only cause suspicion, but this would also be incriminating in some countries where encryption is illegal. In other words, while cryptography protects only the contents of a message, steganography is capable of protecting both messages and communicating parties.
One drawback of using steganography is that it takes a lot of overhead to hide relatively few bits of information. Also, once the system is discovered, it becomes entirely worthless. However, one way of overcoming this possible drawback is encrypting the text first before concealing it, which is exactly what we're doing in our case.
In our case, we are using the library LSB steganography. The idea is to store information in the first bit of every pixel's RGB component. If every first bit has been used, the module starts using the second bit and so on. So basically, the larger the data, the more the image is altered. In that library's implementation, first, the size of the text is encoded within the image, and afterwards, each character of the text is encoded one by one. Since we are the ones generating the images for each encrypted text we receive, we always ensure that the image size is 10 times as big as that of the text.
Suppose that the user Mariem decided to send the message, "Hi everyone," to all the users. As we explained previously, before this message gets sent from the client side to that of the server, it gets encrypted first, then concealed within this randomly generated image. This is the image that was generated after the message got concealed within its pixels. As you can tell, it's very hard to tell the difference between the two images before and after the steganography. Supposing that the image was somehow intercepted by a man in the middle, not only will he receive this randomly generated image, that wouldn't make much sense to him, it would be very hard to tell that there's a hidden message in the first place. However, supposing that he manages to somehow to decode the concealed message, this will be the retrieved message. The encrypted version of the message, "Hi everyone."